Today we're going to talk about a subject that's a little more complicated than past, and that's waveguides. I could do this with PowerPoint or OneNote or something, but I prefer to go from scratch. So I'll try to explain some of the things that you really have to appreciate about this. By the way, before I even start this, were there any questions about the prior homeworks? There are two types of things we're talking about when we had oblique incidents. We could either have TE or TM polarizations, right? And there are sets of equations that are different for each, for the reflection and transmission coefficients. There's similarities, but there's differences. Now, both of those equations for the reflection and transmission coefficient become the same thing if the incident angle is 90 degrees. Do you understand? Because then the sine of 90 is 1, so you literally get a to 2 minus a to 1 over a to 2 plus a to 1 in both equations. Just remember that. But with TM polarization, you get that one angle. Brewster's angle is where you get total transmission. You don't get that with TE. Remember that one fact. And TM means that if you were, say this is water down there, this surface was water. So if I was propagating, the magnetic field vector would be in this direction. Do you follow me on this, class? This is going to be TM. The electric field will have components. If you think about E cross H as direction of propagation, the electric field would have, that's the Z direction, that's the X, right? And Y is this way. H is out, and this marker is indicating H. This is TM. It's a transverse magnetic to the plane it's propagating in, right? But it's also parallel to the interface, if you know what I mean. So now when that strikes, there's going to be at the Brewster's angle, if it's TM polarization, then all the energy propagates into it. You don't get that with TE. Remember that one simple fact. TM with TM polarization. That's important. All right. And you had Snell's law. And there are no questions about that. I only gave you a couple of problems, and they're simple, right? Yeah.
Could you work one of them, please?
Snell's or which one?
From the last homework, 6.48.
All right. You're gonna have to tell me the specifics.
It says a 100 megahertz TE polarized wave with amplitude 1 volt per meter is incident from air.
1 volt per meter, and that's E incident.
Yes, sir.
Go ahead.
Is incident from air onto a slab of lossless non-magnetic material with epsilon relative equal to 25.
You relative 1?
It doesn't specify.
And this is air?
Yes, sir.
What angle is it coming in at?
40 degrees.
40 degrees, all right?
And it asks to calculate the angle of transmission, the reflection and transmission coefficients.
How is the field polarized? This would
TE.
be either TE?
Yes, sir.
All right, transverse electric means the E field here is out of the board, and this would be like the X direction. What I'm doing is I'm having this propagate this way, so it looks like it's hitting water. Are you with me, class? That's the angle of incidence is 40 degrees, and they want the reflection transmission coefficients, or the amount of field transmitted and reflected.
Yes, sir. They want the angle of transmission and the reflection and transmission coefficients and the incident, reflected, and transmitted fields.
So this is a TE mode, right, class? For TE mode, I'm going to go through this. First, we'll use Snell's law. Snell's law says what? Beta 1 times sine of theta incident is equal to beta 2 sine of theta transmitted. Do you agree with me, everyone? Now, in our case, the incident angle is known. We need the transmitted angle. That's this angle. So if we take beta 1 by beta 2, we would have beta 1 by beta 2 here times the sine of the incident angle, and then we take the inverse sine of it. It would be sine minus 1 of this would be actually our theta transmitted. So when we look at beta 1, that's equal to omega times square root of mu 1 epsilon 1. Beta 2, if we divide them, would be equal to omega times square root of mu 2 epsilon 2. Everybody follow me what I'm doing here? Now you'll notice everything cancels except the epsilons. Here, the epsilon in this media is 1, right? The epsilon relative is 1, but the epsilon relative in that media is 25. Agreed, class? So if you look at this, the ratio of these two becomes simply the square root of epsilon 1 over epsilon 2, and that's 1 over 5, because it would be 1 over square root of 25, or 1/5. You agree with me, everyone? Now I go ahead for this one and I say that that angle is going to be the inverse sine, or sine minus 1, of this ratio, which is 1/5 of the sine of 40 degrees. I wish you made the 45, but 40 degrees. So what's this angle? It's going to be small. It's going to be around what, 8, 10 degrees maybe, or less? Could you do this? Just check me on this one, guys. Did you do it? Or you just look at the answer?
I can't remember correctly, 7.5.
Can anybody just punch that for me? Just make sure.
7.386.
That's close. 7.386 degrees. So now we have our transmitted angle, right? Next thing we need is the reflection coefficient. All right, this is the reflection coefficient for TE. Now, I always tell you, if you need to kind of get a mental help, sort of a little mental trick that helps you remember this. I know I'm always going to have a to 2, and I'm always going to have a to 1 here, and there's a subtraction sign. I'm always going to have a to 2 and a plus sign here, and a to 1 here. Correct, class? It's always the media I'm going into. And then I know for TE, it's a to 2 times the sine of theta, cosine, right? No, I'm sorry. Sine, in this case, sine of theta incidence, and this is going to be sine of theta transmitted. This is, wait a second. Our book uses see, I teach radar too. This angle is, the angle we're using is with respect to the normal, right? Isn't that right? I mean, it has to do with this angle and this angle. That means these are cosines, sorry. So it's cosine of theta incident here, and this is cosine of theta transmitted. This is cosine of theta incident. This is cosine of theta transmitted. Look this up. Did you all see that formula? I'm sorry, because here's what you gotta understand. When I teach radar, if you use this angle, it's the one that's not measured with respect to the perpendicular, but measured with respect to the plane of the ground usually. That's the angle. Just say so it would be a cosine there, I mean a sine there. You all see this right there? Now, you'll notice when we have a to 2 and a to 1, a to 2 is equal to the square root of mu 2 over epsilon 2, and it's because it's lossless, and a to 1 is equal to the square root of mu naught, really mu 1 over epsilon 1. But if I divide top and bottom, if you listen to me, by a to 1, I get rid of this, then I make this a to 2 over a to 1, make this a to 2 over a to 1. Now, why did I do that? Because I know that a to 2, right, is really the square root of mu naught over 25 epsilon naught, because the relative permittivity is 25. Agree, class? It's mu, and I know a to 1 is equal to simply square root of mu naught over epsilon naught, and I know the mu naught over epsilon naught will cancel. So when I get this a to 2 by a to 1, I get 1 over the square, I get rid of the mu naught and epsilon naught, and I get 1 over the square root of 25, or 1/5. So this becomes 1/5. And now we have the incident angle as 40, we have the transmitted angle as 7.386, and then we have these coefficients, so you can punch the numbers, and what do you get for this? You'll notice it's a real value, but it could be negative, couldn't it, class? It will be negative, isn't that right, class? Well, I don't know, actually. You agree with me, class? What do you get for this? Just do the calculation. By the way, I'll promise you this. If you don't do a couple of these, on the exam, chances are you're going to make a mistake. There's something about this kind of equation. I see that with the Zn equation. You have Z naught times the quantity ZL plus J times Z naught tangent of beta L over Z naught plus J times times ZL times tangent of beta L. When you do those kind of equations, people make mistakes on their calculators, left and right. Do this equation, just tell me what you get. Remember, that's incident, that's transmitted angle. This is negative, I'm almost positive. It is negative. Well, it better be negative.
And so negative 0.712.
Anybody else confirm or deny? How many got that? You got it? Anybody else? You got it? All right, now that's the transmission coefficient, right? I mean, the reflection coefficient, my bad. What's the transmission coefficient? This is nice for the TE, the transmission coefficient is 1 plus the reflection coefficient for this case, right? Yeah.
Here, is it just coincidence that the beta 1 over beta 2 equals the beta 2 over beta 1?
Well, it has to, because if you look at the definition, beta 1 is just omega squared and mu1 epsilon 1, right? All right, well, that's beta, omega's canceled, you see that? Mu and both are the same. So it's gotta be just related to the square root of epsilon over epsilon 1, epsilon 2. If mu is the same in both of its losses, it's always gonna be relative to the square root of epsilon relative 1 over epsilon relative 2. Always. Follow me, class? All right, now, help me out here. Do you all get this right here? And what do you get for this?
0.29.
All right, now with that, look, we got an incident field of 1 volt per meter. That means the transmitted field's magnitude is going to be what? The transmission coefficient 0.29 times 1, or 0.29 volts per meter. You all see this? The reflected field's magnitude is going to be, magnitude is 0.712, but the sign is negative. You follow me on that one? Now what you can do is you can also write this as 0.712 e to the j, and then you could put pi here for radians. That's 180-degree phase shift. That makes it -1. Follow me? Or you could put e to the plus or minus j 180, and sometimes they get fancy and they'll do this. They'll have an n pi, where n is any integer value. That can't be n, sorry. It's gotta be 2n plus 1. That'll make it odd, where n is any integer value. Do you follow me on this, class? They do something fancy. You don't need to make it that fancy. Just leave it as -0.72 and put that in with a coefficient for where you have E naught transmitted. You know the equations? But I don't expect you to give me the equation with all that buzz, where e to the, it'll be minus j beta times x sine theta transmitted plus z cosine theta transmitted. Do you follow me on this, class? I'll just ask for the magnitudes. All right. And the reflection, I'll ask for the reflection transmission coefficient, transmitted angle. One other thing I would get to, I want to make sure we're clear on this. What's the transmitted power density in region 2? This is important. Well, what is power density in any region? I call it SAV, right? That's PAV, but what is it really? That's 1/2 times the magnitude of whatever electric field you're talking about squared divided by the impedance in that region. That's generally true for lossless, right? Lossless, remember? All right, so that would be, for the second region, it's 1/2. Now the electric field would be the transmission coefficient times E naught incident, right, squared, over the impedance in the second region, which is what? It's the square root of mu over epsilon, which is really the square root of mu naught over epsilon naught, times the square root of 1, right, over 25. You all see what I'm doing here? I broke out the mu naught, epsilon naught. Mu relative is 1, epsilon relative is 25, right? Now what is the square root of mu naught over epsilon naught? 120 pi, right? 120 pi, or 377 divided by square root of 25 is 5, right? So really, this down here would be equal to 120 pi divided by 5. And that would be the power density transmitted. Do you follow me? Since E naught is 1, it's tau squared, which is 0.29 squared. We might as well do this one. 0.29 squared over 2 and then it's 120 pi over 5, and I don't know what that is. Anybody? Y'all see what I'm doing here, right?
I got 0.5 milli.
Okay. 0.5 times 10 to the minus third watts per meter squared. Anybody confirm or deny that? That's what you got?
Yeah, that's what I got.
Okay. It would be the same for the incident wave. You would take the electric field, square it, divided by 2 and 8 and up, and same for the reflected wave. Interesting thing about this, when you do that, you're going to see something weird that happens. It's not conservation power, as you might think. Now, here's why. It is for the normal incident case. What they usually do is this, the way they show it. Normally, you put a tube in here with a certain width, all right? Now, what happens is, of this width, there's a certain amount of power flowing in it. You follow me? If you think about that power, there's a certain amount of power in that tube. Think of it as like a coax cable. Now, some of that is reflected, and that power is coming this way. But some is transmitted. And here's the thing, I didn't show this quite the way I wanted to. But what you're gonna see is, if I would do this a little better, let me make it really exaggerated. Look at the cross section. This is the cross section, the power's flowing through here. This is P incident. Do you see that? Now look at the cross section, it's transmitted. The cross section is much wider. Do you see that? And look at the cross section here. This will be the same cross section as this one. But this power through here, the total power that penetrates this, give it some width D, and this some width D. This power will either be reflected that way or transmitted this way, but this is much wider than D. Do you follow me? And that's the way you get conservation of power. You literally have to build a little tube like that, and you'll see that within these tubes, their power is conserved. But the actual incident power density isn't equal to the reflected power density plus the transmitted power density. Remember that. That's very important. All right? So I'm just warning you about that because that's a common flaw. It's with these tubes. I don't usually cover that. I can, if I have time at the end of the course, just to show you something. And by the way, how would I get this? This cross section we call D. Normally you make D1, right? Okay. Now what's this cross section? If this is 1, what's this? Just think about this angle. This is, this would be the incident angle, right? So this is the incident angle minus 90 degrees, correct, class? Y'all see how here that this is, if I want that angle, it's opposite over hypotenuse is the sine of that angle. So this distance here is actually D divided by the sine of whatever this angle is. I'll call it alpha. That would be this. And then what you do is multiply the power transmitted that way times d sine of theta plus the power transmitted this way, which is reflected power density, because this has the same cross section as this, is equal to the incident power density. But that's for another time. It's interesting though. All right, next thing, I don't know if he talks about that in his book. Did that answer your question?
Yes, sir.
All right. Now on to waveguides. Now we're going to do the rectangular waveguide. Let me explain one thing about a waveguide. What it amounts to is this. A waveguide is something that is much like, if you think about a very long pipe that's rectangular. You've never had this experience, but if you shout down a very long pipe, only frequencies above what are called the resonant frequency in that pipe, you can hear at the end. You can't hear anything lower than that. The reason is they get damped out. Now, when I say resonance, does everybody understand that concept? Basically, like if you have a bell and you ring it, the frequency it rings at is called a resonant frequency. It rings down here, bang, basically decreases. When you have a resonant cavity or resonant circuit like an L and a C, then the frequency that that thing would ring down with, if you blast it with some voltage, would be 1 over the square root of LC would be omega, and 1 over 2 pi divided by the square root of L, 1 over the quantity 2 pi squared of LC would be the frequency in hertz that it would ring down at, right? So if you had an actual cube, metal cube, and you had a small hole in the top and you could pierce electrons in there with a shot, then it would be like kicking a bell, and that cube would ring, the electromagnetic waves would move in such a way to set up a resonant structure at the frequency associated with the resonance in that cube, which we're going to do. When you have a waveguide, it's the same thing, but the ringing is just between the walls, all right? And the wave propagates down the guide. But you can't propagate at any frequency. It's going to have a cutoff frequency. The only thing that will propagate in a waveguide has to be above that cutoff. It's above a certain minimal frequency. Everybody okay with this? So now back to the actual adventure we're on. So for a waveguide, it's a piece of pipe. So just draw this. Put in a coordinate system. This would be X, this is Y. So X cross Y is Z. So Z in this case is coming out of the board. It's coming this way. And what we do with our little waveguide is this. We draw it like this, and we're going to say that this guide, this isn't a very good drawing, but basically you're going to have a dimension in the X dimension equal to A, dimension in the Y dimension equal to B. And this is going to be conducting on all edges. So if you think about this pipe, just think of it like this. It's a long piece of pipe, like such. And it has that cross section where this is A and this is B. And it's got, for all intents and purposes, L you can think of looks like infinity for now. It's very long. Got me? So what we're going to do here, we're going to forget about the Z coordinate for now. We're going to focus on this X and Y dimension. This would be the origin, 0, 0 here. This height is B. And now what goes on inside here? Now, I don't want to make this overly complicated, but you all remember when I decided to go ahead and talk about a plane wave, you don't write this down, just listen to me. I started by saying with Maxwell's equations, I have curl of H, and this is lossless. We're assuming sigma is 0. We're going to assume for now that we're in the phasor domain. So we had curl of H is equal to J omega mu times E. Don't remember that? We substituted in for D, epsilon E, and then the time derivative brings out a J omega. And then we had another one. We had curl of E equal minus J times, this is epsilon, my bad. I should have yelled at me for that. Mu omega times H. Do you all remember that? That's normally this is B omega minus J omega times B, but B is mu epsilon. And almost always we deal with E and H when we write equations for field quantities. In terms of one equation, of only one variable, either E or H, it'll be either E or H. It won't be B or D usually. So now if you take this, I did the curl of E, because I want to write the E equations is equal to minus J omega mu, right, times the curl of H, which is J omega epsilon times E, and I have J times J is minus 1, makes this a plus 1, and then I get omega squared mu epsilon times E is equal to this, and this is the gradient of the divergence of E minus del squared of E. E in this case is a vector quantity. You remember this basically without all the intricacies, doing something like that? This is a vector identity of a Kroll operator. Now, one other thing we do, we say that it's charge-free, or the volume charge density is 0. Does anybody remember why I said that? I know it's a Friday. Anybody? There's one particular thing we can simplify. Take a look at that divergence of E. What is divergence of E equal to? Divergence of E. Let me go a step back. What is divergence of D equal to, generally? It's important. That's the point form of Gauss's law, isn't it? All right. So, or the differential form, that's rho v. Well, if rho v equals 0, right? Divergence of D equals 0, right? And divergence of D means D is equal to what? Epsilon E, right? So that means divergence of E is rho v over epsilon, and that means that's 0 too, which means this goes away. That's my whole reason for saying that. This is a simplification factor, which brings me to the point where I was with the waves in free space. Now I get this equation. It's going to be that plus omega squared mu epsilon E equals 0. You can write that one down. That's the equation we solve in waveguides. And we do it in Cartesian coordinates for rectangular guides, cylindrical coordinates for cylindrical guides. Now, here's some important bits of information. Dr. Whitworth introduces a term, beta, but he puts a subscript mu. And this is what it is. This right here is called beta unguided. He calls it beta unguided squared, which means beta unguided is equal to omega times square root of mu epsilon in the guide. So he uses U to indicate unguided. It's free space. Like if you had a wave in free space, not stuck in a wave guide, that would be the beta, wouldn't it, class? Beta is also 2 pi over lambda. If you do any outside of the book reading, you'll see 2 pi over lambda squared put in there. You'll see all sorts of variants on this, but this is beta unguided, okay? Now, when we have a waveguide, we have x, y, and z coordinates, we talk about 2 things. Please listen to this. Remember, z's coming out of the board, right? Now, there are 2 modes of a waveguide. We call it either TE or TM. Now, TE before meant what? That the electric field was transverse to the plane it was propagating in, right? Like if it's propagating, the wave's propagating in that direction and pointing this way, that's TE, correct, class? If that was a magnetic field, it would be TM, correct? There's one other factor I want you to think about. If a wave is in this direction, if the H field, if it's TM, in this direction, you see there's no magnetic field in the direction of propagation. You all see that? Are you with me? TM means, E is this way, right? E cross H would be the direction of propagation. You all see what I'm talking about? That's the direction it's propagating. There is no H field in that direction. Do you follow me on that, everybody? Now here's sort of why I'm saying it. Just assume this is the cross section of a guide, and this is the Z direction. Now if you have a wave that's TM, the magnetic field's coming out, but the electric field could be in this direction, and this is something I'm going to show you. The magnetic field's out, that's the electric field. Now you'll notice that the way the waves travel, they bounce here, then here. This is the path. And really you have the superposition of waves. This is one, but there's also, at the same time, there's a wave going this way and bouncing this way. Are you with me? Now this is TM mode, TM, transverse magnetic. The magnetic field is out, all right? The E field smashes there. The E field's got a component in the direction of propagation. Do you all see that? Why? Because of the way it's ricocheting. It's bouncing this way, this way, this way, this way, this way. So there's no magnetic field in the direction of propagation, but there is an electric field. Can you appreciate this? This would be for the TM mode. And thank God for the TM mode. It means there's no electric field in the direction of propagation. So what we can do, we can use that to our benefit. What we can do is this, and I like working from here. I don't like Dr. Wimmer's book. I'm sure he has a method for how he does this, but let me just explain this chapter what he does. He starts in the beginning and he says, well, here are the equations that describe cutoff frequency and of a waveguide. But he doesn't explain where they sorry, I'm gonna just kill that. I forgot to shut my phone off. Hello? Yes, I'm in the middle of teaching a class. Can I get back to you? Yeah, call me back at 2:30. Bye-bye. The only reason I took that call, this has to do with a lawyer and doing some consulting for a case. It's a civil case in New York City, so I had to take that one. I apologize. Normally I don't take calls. Anyway, y'all see what I'm doing here? Now that we've established there is no, if we're going to, now just write this down. This is the TM mode. Dr. Whitworth does this. He gives you a lot of equations. He doesn't use first principles to derive them. He does later, but he just throws that out there. And he sort of says a waveguide is just something that focuses electromagnetic power down a tube. And that's the truth. But now it gets better. For the TM case, realize this. Their Hz equals 0 because the Z direction will be the direction of propagation. The wave is confined between X and Y. It propagates in the Z direction. Are you with me? Now, once we do that, then we can do this. And this is such a powerful thing. Remember when you have this, the del squared of E plus beta unguided squared E equation. E is a vector, right? So really this is going to be the del squared operator on EZ plus beta unguided squared EZ, all AZ plus, and then you would have the corresponding AX and the corresponding a y component, all equal to 0. You would have the del squared operator here. I might as well put them in one time. EX plus beta unguided squared EX plus del squared on EY plus beta unguided squared EX. All those equations, I'm sorry, this is Y, would be equal to 0. But the only one we care about is this right now, because we know there is no magnetic field in the direction of propagation, so we can use that for our benefit. Work with me on this one. So we get rid of all these others. We don't care about those. That's still all true, but the only thing we focus on is this. Now the del squared operator means this. It's the second derivative with respect to x squared of EZ plus the second derivative of EZ with respect to y squared plus the second derivative of EZ with respect to z squared. All that plus beta unguided squared EZ equals 0. Try to appreciate what I've done. I've taken this vector quantity and I've replaced the del squared operator with its definition. If you look at the back cover of the book, just flip it there, you're going to see something that's called the Laplacian. Frankly, that's a scalar Laplacian, but for our case, because we're operating on only EZ, it'll work here. Y'all see that? It's called Laplacian. Is that the last thing we do? Very last thing. Look at rectangular coordinates Laplacian. This is at the cover. It's on, no, back cover, other way. Go to the very back. See it? Very bottom on the right-hand page. See it down there? Laplacian. So that's what I'm doing. Now I've written it down. Now here we're going to do something you haven't done in a while. Do you remember separation of variables back in differential equation theory? Anybody hear that before? You did separation of variables, didn't you guys? Remember back in the day? Why was that powerful? Because you can then get unique equations and solve them instead of having a mixed bag. Now, I want to say this. EZ in general, write this down, is going to be some function of x alone. And I draw that by putting a capital X with an argument of x. And it's some function of only y alone. We're assuming this, of course, times some function that's only a function of z alone. So what I'm saying is that EZ we're assuming can be written as just a function of x, like sine of x, just a function of y, and just a function of z. We're making a guess. Now the way we can find out if our guess is justified is we take this and do these derivative operations and then see in fact if it solves that equation uniquely, all right? Without any mess. And I'm going to do that over here because this takes a little room. This is kind of interesting. When I was sitting where you were, I remember I had a guy named, his name was Dr. Brody, and what he did was, he was a mathematics professor, and I remember him inviting me to a special mathematics course where they're gonna develop something called the symmetric derivative. I'll spare it all. During that special topics course, I was only a sophomore, I got to appreciate mathematics. Mathematics used to irritate me a lot of times because it seemed like memorizing a whole lot of formulas when I was in high school, geometry stuff and stuff. But then I got to appreciate the beauty. It is a very descriptive language, and there's intricacies that there's a very logical layout to mathematics, the way it's done. Anyway, for this, we're going to take a guess at this solution. We're assuming we can write just the function x, function y, function z. Now, here's something. When I take two derivatives on that with respect to x, the only thing that I get to derivative is the x. Follow me? Y and z are like constants. So I can write that first term, second derivative of ez with respect to x squared, I can just write as double prime x, right? Then times y of y times z of z. Does that make sense to everybody? I'm putting the two derivatives as two dots there. I know it's with respect to x. Then I've got that plus double derivative of y, right, times x and z. Y of y, x of x, times z of z. And finally, then I have a double derivative on z times x of x times y of y, right? And that's all plus beta unguided squared x of x, y of y, z of z, all equals 0. Y'all see what I've done? This is where it gets good. Now remember, we're trying to solve this thing. So what we're going to do is divide everything by capital X, capital Y, capital Z. And in doing so, watch what happens. If I divide this by capital X, capital Y, capital Z, the Y and Z go away, right? And then I get this. I get x of x over x double prime divided by x. Do y'all see that, class? Now I divide this by x, y, and z. What am I left with? Y double prime divided by y of y, right? And then I divide this by x, y, and z. It gets rid of the x and y. And I have z double prime divided by z as a function of z. What happens here?
Just left with beta squared.
That's right. I'm left with beta unguided squared equals. All right, now here's some more. So now I've got this equation. You'll notice, though, this is very interesting. I have a function of only x here, right? Admittedly, it's derivatives on x, but there's not a function of y and z. This is my guess. I have just a function of y here. Not a function, doesn't matter what x and z are, correct? And over here, I have just a function of z, which doesn't depend on x or y. And over here, I have a constant, which doesn't depend on anything, which is just what I want. Now, the reason I'm saying that, the only way you can have an equation that's a function of x and a function of just a function of x plus just a function of y plus just a function of z plus a constant equal to 0 is if these are constants as well. Otherwise, it'll never work. That has to be a constant. It has to be invariant of the value of x. Do you follow me on that? This has to be invariant of the value of y, invariant on the value of z, or x or y. So what we can do is we replace this term with, or we really call this term right here, just follow me on that. We call that minus kx squared. Write that down. Now, in Whitworth's book, he's going to use beta x, but I like k. And here, we call this term minus ky squared. And in here, we call this term minus kz squared. And this term we simply call beta unguided squared equal to 0. Now this is the equation we're going to solve. So now we replace these terms with that. And I have kx squared, I have minus kx squared minus ky squared minus kz squared equals beta unguided squared. Are you with me? Please try to appreciate what I'm doing. I'm not trying to make this complicated. I'm trying to show you how come it works. Next. It's a bomb. We get to this first one, we get x double prime over x is equal to minus kx squared. That's my claim, correct, class? I'll multiply both sides by capital X, and then I'll bring them all to one side. So I have that plus kx squared x equal to 0. Are you with me? Now what does that double prime mean really? Well, it means the second derivative of x divided by x squared plus kx squared function of x equals 0. So this function of x now has two derivatives plus a constant, kx squared, times itself, equal to 0. This is a simple, what? It's a second order linear homogeneous differential equation. If you remember back in the day, the way you always solve these things, you let x be equal to some constant e to the lambda z, or lambda x. Y'all remember this? Then you took two derivatives and you get a lambda squared out here, right? X plus kx squared x equals 0, and you found out that lambda squared is kx. And so make a long story short, the solution to this would be x of x could be either, it could be some sine, it could be a sine of kx times x. It could be a cosine of kx times x. Either of these will solve it, or it could be e to the plus or minus j kx times x. Any of these terms could solve it. Do you follow me on this, class? You put a cosine in there, it solves it. You put e to this, it'll solve it. You put a sine, it solves it. They all solve it. Got me on this? So which one do we select? And then we go back to the waveguide, the way it's drawn. When we have a waveguide here, this is the x-axis, and that's 0, and that's equal to, I'm going to call that distance A. Do you remember I made this bottom distance A? It's consistent with Dr. Moore's book. Are you with me? All right, well, what do you know about this? This is the E field in the Z direction, right? Now, if that's X and this is Y, Z is out of the board, isn't it? Please keep an eye on this. This is a very important point. All right, now when X is 0, the E field would be in this direction, right? Wouldn't that be parallel to a conducting surface? Because isn't this really a rectangular pipe coming out of here? It's conducting. So if EZ is right here and it's 0, well, does a cosine of 0, is cosine of the argument 0, 0? No, cosine of 0 is what? Cosine of 0 is 1, right? That means no matter what the coefficient was in front of the cosine, unless it was 0, it wouldn't work. So cosine doesn't work. The other thing is that exponential, if I have plus or minus j ever 0, for any real argument of x, no, right? It's just what? It's 1 at some angle, isn't it? So the only thing left is sine, and that's because it's got to be 0 there. So then we say our x of x will have the form of a sine of kx times x. Now I'm going to tell you this. I didn't put any scale factor in front of there because that comes at the end. We could put a scale factor, couldn't we? Now that meets this boundary condition right here, right? We know that EZ has to be 0 there, don't we, class? Where else does the E field in the Z direction have to be 0? At the other surface right here, doesn't it? Right? And where's that distance at? At A, correct, class? So we need to say that it's not just sine kx equals 0, but it has to be sine of kx times A has to be 0 as well. Do you follow me on what I'm doing here? This is the second boundary condition. Y'all follow me? All right. Now, when is that true? When is the sine 0? When the argument sine of 0 is 0, right? Sine of pi, right? Right. Now, if I was handing out dollar bills for right answers, I'd get a lot better response, but I'm not. So really, when we have really kx times a equal to just pi, when else is it 0? It's 0 at pi. When else? 2 pi? How about 3 pi? How about n pi, or m in this case? He used, Whitmore's book has m. So that means my value of kx can be found to be m pi over a. Any integer value of m will get me a value of kx according to this formula to work. So that brings me to my next point. Now I can say x of x is founded, the function, and it's going to be equal to the sine of m pi over a times x. Are you with me? That's the variation in x. If you're looking at your book, he has this. Can you tell me the page number it's on?
389.
What's your first name? I'll try to learn the names.
Trent.
Trent? Trent. All right. I know Josh. What is yours? What?
Keaton.
Keaton. Try to learn that. And in the back.
Justin.
Justin. Keaton, Justin. Trent. Just try to get 3 down for a second. I'll work on the rest. Well, I'll get there. All right. So we got the x variation. How do you think we get the y variation? Take a shot in the dark. We go here, right? Replace everything over here. The x terms with the y. This is now ky, right? This is going to be the y variation. Y double prime over y. And then that equation will lead to the second derivative with respect to y of the function of y, right? Just y, plus ky squared of y equals 0. And that, in fact, has the solution that y of y could be a sine, could be a cosine, but could be e to the j plus or minus j ky times y. But the only one that will work is going to be the sine of ky times y. And the reason that's the only one that will work is because, again, for this one, this is representing the y of y is what? Is a component of ez, right? We separate it in terms of functions of just x, functions of just y, functions of just z multiplied together, right? And we know that represents ez, and we know ez here at the lower surface, right? When y is 0, this is a y, it's 0, so the sign has to work, right? Because sine of 0 works. But it also has to be 0 at b, doesn't it, class? So that means what? If it's 0 at b, the sine of ky times b equals 0, correct? So what is ky times b going to be? Well, when is the sine 0? 0 at pi, no, pi over 2, it's 1, isn't it? Sine of pi over 2 sine 90, it's 1. At 0, at pi, at 2 pi, and really at, how about n pi, where n's an integer. And therefore we can get ky is simply equal to ky is equal to n pi over b. And lo and behold, that works. So now I have my variation on y defined. Now for the variation on z. This is the important one. X and y are just sinusoidal variations in terms of the magnitude of the EZ component of the electric field. But now if you think about this, when we talk about, remember, we got an E field in the Z direction, right? We have to figure out a way to get the boundaries for that. Now I'm just going to tell you the bottom line of this. The E field in that case, as it's going up and down, it's got an unlimited range. We have no boundary conditions per se. The thing is, it's also propagating in that direction. Do you follow me? Whenever you see a propagation term, you know you're going to have this exponential formation to it. So in general, the Z component, I could write the equation just like I did here and then say it could be a sine, it could be a cosine, it could be e to the plus or minus kz times it. But the only one that works is e to the plus or minus j times kz times, okay? That's the one that works. And that all said, let me just write the final form of this. So now, when we take all these forms of x, y, and z and we multiply them together, just like the separation of variables says we are to do, this is laid out in his book. He doesn't do it quite the way I do it, and I'll try to explain. I mean, he does, but I use I use KZ there. Now my general form for EZ, this is for the TM mode, is going to be some constant. So just write E naught here. It's some scale factor. And it's going to have a variation as sine of M pi over A times sine of n pi over b, where m and n are integers, times e to the minus j, and here kz times z, and that's the E field in the z direction. I'm going to explain kz in a second. And you'll appreciate this. Remember, we had the equation minus kx squared minus ky squared minus kz squared, and then we had plus beta unguided squared equaled 0. Do you remember that? That's when we did the derivatives, right? And we divided by x, y, and z, right? And we went in and we put the constants down for x double prime over x and y double prime over y, right? And z double prime over z. Now, I want you to notice this. We know what kx is. It's what? It's m pi over a squared, right? We know what ky is. That's n pi over b squared, right there. And we know what beta unguided is. It's what? Omega squared times mu epsilon, all right? So watch this. To find out what kz is, kz would be equal to the square root of beta unguided squared minus kx squared minus ky squared. That would be what kz would be. And Dr. Wentworth's book calls this just beta. And the reason he does is because beta is the propagation constant in the direction of the z-axis, in the direction the waves propagate. Follow me? It's not unguided. It's the beta that has to do with the wavelength and the direction of propagation. This is important. So what is this going to be? The beta in Dr. Wentworth's book is kz is equal to the square root. Well, beta unguided is omega squared times mu epsilon minus kx squared minus ky squared to be minus the quantity n pi over a quantity squared plus n pi over b quantity squared. And that would be beta squared. Now that beta is kz. This is important because this is the thing that gives you wavelength along the guide and stuff like that. So write this down. Can y'all read this?
It's in the book too,
What page?
389 at the very bottom.
All right, watch. This is going to help you. All right, now follow me on this. Remember this form right here. I want you to look at it for a second. You see where kz is? And I mentioned something called cutoff, didn't I? Now, when you think of beta in general from before, beta was 2 pi over lambda, right? Now, when we're at cutoff, it means the wavelength in the guide goes to infinity, or it means beta goes to 0. All of a sudden, it doesn't propagate. You follow me on that? If this is 0, right here, that means it's got no variation in z, and that means it doesn't propagate. Basically, it doesn't fit. And the real truth about this is Dr. Shumpert, professor years ago, used to say this. He goes, it means the wave is too fat. It is too low of a frequency, or that sinusoidal shape just won't squeeze into the guide, so it'll be shorted out by the guide. That's what it comes down to. And what that really means is the beta, this beta goes to 0, and put this down at cutoff. This is the lowest possible frequency that you can go at. So what is cutoff frequency? Well, it's when a wavelength goes to infinity, or it's when beta goes to 0. So how do I figure out what that amounts to? Now watch this. So I know this equation is 0, don't I? Right? I can throw the square root sign out the window, can't I, class? So now I have this. I really have omega squared times mu epsilon is equal to m pi over a squared plus n pi over b squared. Only thing I'm doing is this is the equation that happens when AZ equals beta equals 0. This is at cutoff. And make sure you understand this. This is an important point. All right, well, I'm going to do this right here. You can just watch me. Don't have to write this down. Y'all agree I can divide both sides by 1 over mu epsilon. Y'all give me that? Right? Now the next thing I'm going to do is take the square root of both sides. So now I do this. And that would be omega. Write down omega c here. C for cutoff. But what is omega in terms of f? People?
2 pi.
It's equal to 2 pi f, right? And that f would be f cutoff. It would be the frequency below which I couldn't propagate a wave. So then I can write f cutoff as this. I can say it's 1 over 2 pi times the square root of mu epsilon in the guide times the square root of m pi over a squared plus n pi over b squared. And this is the cutoff frequency in a waveguide defined. Now I'm going to show you one other thing too. In general, when you think about 1 over the square root of mu epsilon and you're in a lossy media, or a lossless media, what do you think about? Well, what if you're in free space? What's 1 over the square root of mu epsilon? Anybody? What's 1 over the square root of mu epsilon? Let's make sure we don't forget this. This is actually a very famous term. Remember what phase velocity was? It was omega over beta, wasn't it? Right? All right. Well, in lossless media, it's omega over the square root of beta would be omega square root of mu epsilon, right? Right? So y'all see the omegas cancel in that one. That's phase velocity, right? What if it's free space? What's the velocity of light in free space? C, or 3 times 10 to the 8. Well, that's 1 over the square root of mu naught epsilon naught. And if you don't believe me, you can prove it to yourself, because if you take a look at that, that's 1 over the square root of mu naught. That's 4 pi times 10 to the minus 7 times epsilon naught. Epsilon naught is usually written as 1 over, can be written as this 1 over 36 pi times 10 to the minus 9th, right? You all remember seeing that kind of stuff before? What happens when you're done with that? I have what? I'm going to have the square root of 1/9, right? The pi's cancel, correct? Square root of 1/9 is 1 over 3, right? That means 3 comes up, and I'm left downstairs with 10 to the what? Square root of minus 16th, which is square root of minus 8, or I get 3 times 10 to the 8th meters per second. So it's the speed of light. What I'm really getting at is I can replace this 1 over square root of mu naught epsilon naught with this. I can just put c here. I can put c divided by 2 pi, and then downstairs I can put the square root of mu relative epsilon relative in the guide. All right, and generally speaking, epsilon relative and mu relative are 1. Epsilon relative can get a little higher if it's a dielectric, but a hollow air-filled guide has epsilon relative of 1. Follow me, guys? All right, so what do this m and n stand for? Oh, by the way, I didn't do this, but I'm going to do it now. Y'all see how I can take this pi inside and bring it in as a pi squared, then I can get rid of it? So I can get rid of the pi's, thank God. So I don't need those hanging around. And now I have c over 2 divided by the square root of mu relative epsilon relative times the square root of m over a squared plus n over b squared. Is everybody with me? Now, generally, that N and M have to do with the mode numbers. So what I do is put down F cutoff and then put M comma N. And that means, remember how M and N had to do with what? The sine wave variation. If it was a 2O mode, it means in the X direction, it wouldn't have a half a sine wave, it would have a full sine wave and a half, all right? It would be basically have two wavelengths, basically. Or two half wavelengths, a full wavelength. All right, here's something about this too. I didn't say this, but when you look at waveguides, here's what really happens. In the lowest order mode, if this is A and this is B and this is 0, 0, and this is X direction. When you look at the modes, if you just wanted to look at the variation in X, it would be a perfect sine wave right there. It's variation. And it would have no variation in Y for a 1O mode. If it was a 2O mode, then you would get this. Like that. You get a full sine wave for a 2O mode. You follow me on that? And you would keep adding half cycles. If it was a 3O mode, it would start there and go like that. Always starts at 0, ends at 0. And you have to understand, this is the electric field disease variation. Variation this way would be invariant in this direction. It's kind of hard to get this down sometimes, but these are the cutoffs for this. Now, the lowest frequency that can propagate is always the 1O mode if the length in the x-axis is the longest. So, write this down. FC10 is the lowest mode, or lowest frequency mode, or frequency that propagates. And that would be FC, this is assuming that A is greater than B. If it's the opposite, then it's the O1 mode. FC10 would be equal to, 10 mode, would be equal to, look at this, it's the C over 2 square root of mu relative epsilon relative times square root of, you can forget about N, it's 0, it would just be 1 over A squared. Y'all see what I've done here? C over 2 square root of mu relative epsilon relative 1 over A squared square root, which is just 1 over A, isn't it? So this is going to be C over 2A times square root of mu relative epsilon relative. And in general, if it's an air-filled guide, it's C over 2A. C is 3 times 10 to the 8th meters per second over 2A, and A is dimensions in meters. So, give you some idea of it, let's take a look at a couple of cutoff frequencies. I'll show you how to get the other components of B in a second, but all right, so here, if I say FC10, and by the way, the TE mode, this is the TM mode, by the way. This is the TM mode. For this one, let's take a look at the lowest frequency. Well, what would it be? It would be, if we had a guide that had these dimensions. I'm going to give you a typical one. A guide here is going to be, let's see, 5 centimeters, and this is going to be 3 centimeters. So it's 5 by 3, all right? So the lowest order, or the lowest frequency would be C, right? It would be C 3 times 10 to the 8th meters per second over 2. And assume it's air. So if it's air, square root of mu relative epsilon relative is 1. Divided by the square root, or really just divided by A. And A in this case is 5 centimeters, and that 5 centimeters would be what? 0.05 meters, right? We got to put that in meters. So what's that value going to be? Can you give it to me? Well, 2 times 0.5 is 0.1, right? So 0.1 on top is 10, so that's going to be 3 times 10 to the 9th, or 3 gigahertz. Want a class? 3 gigahertz seems like a lot, but that's coming down a guide that's centimeters. Typically, your waveguide is operating just above the cutoff frequency of the guide, of the 1 ohm mode. They don't want a 2 ohm mode, they don't want a 1 mode, they only want 1 mode in the guide, and here's why. We're going to see this. The phase velocity is different for different modes. So if I've got something exciting a guide, and it's in the 2.0, the 1.1, and the 1.0 mode are allowed, all 3 modes get excited, and they all propagate at different velocities, which means the signal is completely corrupted. You don't know how much power is going into 1 mode versus the other, and that's something you don't want. Follow me on this? You only want 1 mode to propagate if you want an uncorrupted signal to come down there. So this is going to be the cutoff frequency in the 1.0 mode for that. You could also calculate the cutoff frequencies for any mode, couldn't you, class? You could calculate the 1.1, the 2.1, and all that. Those are the cutoff frequencies. Now, to get the electric fields and magnetic fields in the other directions, if you look in your book for a second, I don't think I'll have time to do all this, but if you have, we have EZ, correct? And then if you take a look at your book, and I'm not sure of the page, but I'll tell you 1 second. Okay, this is on page 386 and 387. What he does is he goes ahead and he solves the curl V and the curl H equations in terms of their various components, X, Y, and Z. And what he does after you do that, what happens after you do that is basically, I got it done for EY. You're going to get EY, you'll get E, you'll get all the other components. If an EX component exists, they'll all have the same variation in terms of how they vary down the Z-axis. It'll always be E to the minus J, KZ, or beta in his book, times Z. But he shows that very clearly in that part of the chapter. Now, I'm trying to get to a couple of the really important points. This is waveguides. You see, this is quite a bit different than a transmission line. Here, your electric field of transmission line always was what? Magnetic and electric field was always transverse or perpendicular to the direction of propagation, right? The E field was between the inner core and the outer shield, right? That's the way it was pointed. And the H field was also in that plane, right? It was in the theta direction. There was nothing in the Z direction. Here we have an electric field component that is in the Z direction because the wave is bouncing or ricocheting as it goes down there. It's bouncing up and down the waveguide. So it's when the equations are more complicated. Look at how the explanation for the E field in the Z direction is given. And then if you look at the E field in the Y direction, I'll just write this down. I'd have to go through the curl equation to get this, but the E field in the Y direction for this mode in there, for the TE mode, or TM mode, EY is equal to minus J, and this is beta, Dr. Wentworth's beta, over beta unguided squared minus beta squared. And then it's going to be that times n pi over b, and then it's times the sine, E naught, which is a scale factor, times the sine of m pi x over a times cosine of n pi over b times y times e to the minus j beta z. Now, that's a mouthful, and you don't have to remember that. I'm not going to ask you to. That comes from doing the curl of curl business stuff, but he shows that, he lays that out earlier. I don't expect you to be able to derive that, but yet, without any kind of reference, but you should be able to work through it at least once to prove it to yourself. He lays this out in those early pages that I just referenced, okay? It's important you do that. Something else I'm gonna say, I wanna just try to hit all the things. When we talked about transmission lines, which you could say is a waveguide in a sense, but it's not really, because a waveguide means you have wave phenomena that's ricocheting. In a waveguide, you don't have that. You've simply got a plus and minus voltage where the actual wave is propagating that way, but it's not actually something that's bouncing up and down. It's going only in that direction. Do you follow me? Well, in a transmission line, you had something called the characteristic impedance. Do y'all remember that? Here we have something that is likened to a characteristic impedance. It's an impedance in that mode that the guide sees, and it's a ratio of the E field to the H field, which will always be a ratio of the voltage to current that would come on any load connected to that guide, and this is important. So then we get Z in the TM mode. TM, this is going to be equal to, really it's minus it's plus EX over HY, or it's minus EY over HX. And when you do all that, you can thank God you get this. It's beta over omega epsilon. Now that beta is the beta we just found out about. So, what this amounts to, that's omega by the way, omega epsilon. Well, beta was equal to the square root of beta unguided squared, and then it's minus really the well, I'm going to stop for 1 second. This beta unguided is like kx, and it's the square root of beta unguided squared minus kx squared, which is m pi over a squared plus n pi over b squared. And I'm going to tell you right now, I'm about out of time to do this, but what it'll come down to is this. I don't have time to prove this. This will come down to the intrinsic impedance in the guide times the square root of 1 minus the quantity f cutoff over f squared. Now I'm going to explain this. The n here is equal to the square root of mu over epsilon. It's just like in free space. All right, that's like the intrinsic impedance in free space. This is the ratio of the frequency you're driving at into the cutoff frequency, which means the frequency you're driving at has to be greater than 1 for this to be non-negative. Do you all see that? That's real important. If it goes below there, this becomes negative, and then this whole thing, it just falls apart. I'll get to what happens if you try to drive a waveguide at a frequency lower than the than the cutoff frequency. It gets into a mode called an evanescent mode, which is something where the energy rapidly decays and doesn't penetrate at all. But that's for another day and another time. I got about, I think, 15, 20 seconds. Real quick, if that's the if this is the characteristic, or I should say, this is the impedance of the guide in the TM mode at a given frequency, right? Knowing the cutoff frequency of the guide. Then I have a question for you. What do you think the wavelength along the guide would be? We know at cutoff what happens. It goes to infinity, doesn't it? So generally speaking, what you do is get the free space wavelength. The free space wavelength would be equal to like C over F if that would be in a air-filled guide, right? Or it would be the phase velocity in the material if it was unguided, or if it was non-guided, divided by F. And it's divided by then the square root of 1 minus the quantity Fc over F squared. And that's the wavelength of the guide. You can see as Fc approaches F, it goes, that bottom term is going to 0, which means 1 over 0 is going to infinity. Do y'all see that? That's the wavelength in the guide. Now the phase velocity is interesting. Phase velocity is omega over beta, right? Here, the beta term, well, I'm past my time, but this can go faster than the speed of light. The phase velocity is actually phase velocity and unguided, just put it as c over the square root of 1 minus fc over f squared. And I want to tell you this. Phase velocity has nothing to do with the rate that energy travels. It only has to do with something, a point we call a point of phase on a surface. Remember I talked about the ocean wave? Didn't I do that in this class? And I said, if you look at an ocean wave, suppose the wave is like its crest is this way, but it's moving into that shore, moving down here. As it comes in the intersection, I wish I had a long ruler or something. The intersection of that crest with this, you could watch that line moving there. Can you all imagine that? As this starts to become steeper and steeper, even though it may only be moving at 5 miles an hour in this direction, the point where it intersects could be going at 100 miles an hour, right? And as that goes into normal, the phase velocity, where I'm calling the point intersects, the crest intersects, that point could go to infinity. You all see that? Well, phase velocity in a guide has to do with this. When you think about a guide and the cross sections, suppose we have a constant phase surface here moving this way, right? A little bit later it's here, right? This moved a small amount, but here it moved a large amount. Y'all see that? Well, it's basically the phase velocity has to do with the rate that this crest intersects this bottom surface and how fast that thing's moving. That's all the phase velocity is in a waveguide. The group velocity is going to be much less than the speed of light. And the way you get the group velocity is you take simply c squared. If you wanted the actual velocity of energy, you take c squared and divide it by the phase velocity, and you get the actual group velocity. I'll get into that next time, okay? Now, I know waveguides, the equations are a little boring. It's going to make your head spin. So the problems I give you are not going to hopefully make your head spin, but please do read the work. Do read it. And I'm not going to give you a quiz Monday. Probably give you one Wednesday and one Friday to make up the lesson. Do you understand this lecture? I mean, it's hairy stuff in terms of the equations, but